In our discussion of simple harmonic motion, we've limited our analysis to the spring mass system. There's a reason for that. The reason is because it describes simple harmonic motion theoretically perfectly. But nevertheless, we recognize that a simple pendulum is typically an example of SHM. So we're going to look at that for a little bit at this moment. We're going to recognize soon, though, that it is not a perfect SHM system, for reasons we'll see momentarily.
Tick-tock, 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 back and forth, back and forth.
And so goes the motion of the grandfather clock, the pendulum clock. So we have a pendulum of length L, and it displaces theta. The x, which is the displacement from the equilibrium position, is s, arc length. And we know that the arc length is L theta. So L theta is the arc length. And that is the distance along which the pendulum travels. So that's the displacement, or the distance from that equilibrium point. So the path of travel is really what we're talking about. Now, to satisfy simple harmonic motion, we know what the restoring force has to be like. It has to be proportional to the displacement. So the restoring force has to be proportional to x, therefore proportional to L theta. Well, that's great, is it? So we take a closer look. Here we have L theta, x. If we do a free body on the pendulum object, we have mg acting straight down. In addition to that, we have tension. Those are the two real forces. And now let's break them up into components. So we have, at this angle theta, a radial force from the weight, namely this, which is mg cosine of theta. And we also have the force that's actually trying to restore it back to the equilibrium. Granted, it's not pointing to the equilibrium right now, but since the pendulum bob is constrained to move along this path, that is the direction. The force is along the direction of the path at any given moment, and it's always mg sine of theta. So the restoring force is thus minus mg sine of theta. All right. So is that proportional to L theta? Well, not really. It's proportional to sine of theta. All right, so not quite the same thing, not theta. Therefore, not SHM, because it would have to be proportional to theta. However, for small thetas, you know, sine of theta is approximately equal to theta, which is why we have a limit over the angular displacement, a limit on the angular displacement over which we can consider a pendulum to be SHM. So the force is minus mg sine of theta. Now that's approximately mg x over L, x over L. L is here as well. So that would be the opposite over hypotenuse. But you can see that that's not quite exactly the same either, is it? Because it's not a straight line, for one thing. It's a curved path. So we recognize that the simple harmonic motion force is minus kx. But we just discovered what the force is. In the pendulum situation, it's minus mgx over L. Therefore, we can solve for the k, the proportionality constant here, that's just like what we had in a spring mass system. And it's mg over L. mg over L times x. So in that way, it's proportional to x. Well, remember omega. Omega is square root of k over m. Well, here's our k, and we divide that by m, and we get gl. So omega is also equal to square root of g over l. Oh, that's really useful, because now we have the counterpart, the spring mass system omega, square root of k over m. For a pendulum, it's square root of g over l. Now we can write frequency, which is omega over 2 pi, and we have our omega, so divide it by 2 pi, and period is 1 over that, 2 pi over omega. 2 pi square root of L over G. You've seen this before, and now we just derived it. But you recognize that this is an approximation. there were some simplifying assumptions that went into it. Don't even ask me what the period is in an exact expression. I will say, go research it and come back and report on it. How's that? So in this expression, it's independent of mass and theta. Notice mass isn't in there, angle isn't in there. But the rule of thumb is, as I've said in the past, that if the angle is less than 15 degrees or so, then we can assume that this is sufficiently true to call it equals. Well, now that we have the basic idea of a simple pendulum in our repertoire, let us extend this to a physical pendulum or a complex pendulum. Any object suspended as shown, like a wheelbarrow here, will be subjected to a gravitational restoring torque. And we have to just figure out where the center of gravity is. So we're going to pivot it from the end of the handle here. And if we know where the center of gravity is, that's where gravity acts. So at angle theta, this is the path over which the wheelbarrow is constrained, the center of gravity, that is. mgx straight down. And in the analysis of the simple pendulum, we do a similar thing here. Theta, we have a radial force from mg cosine of theta, and then restoring it, mg sine of theta, just like before. But now we also have d sine of theta. D sine of theta, okay, is the perpendicular distance from this pivot to the force. So the line of action, perpendicular to that, we can now analyze the restoring torque. Real simple, mgd sine of theta. Negative there to indicate restoring, opposite of the displacement. For small angle, torque is equal to minus mgd theta for similar reasons as before. Very good. We're well on our way. Sum of the torques is I alpha, so let's make mgd theta I alpha. So minus mgd theta equals I alpha. But what's alpha? You know what alpha is. It's the second derivative of position. So I d squared theta dt squared, which is then equal to minus mgd over I theta. And of course, if you compare this with our standard beginning differential equation for simple harmonic motion, d squared x dt squared is minus k over mx, we have this wonderful comparison.
Hey, if it's got the right form, let's call a spade a spade. Oops, sorry, used that one already. Well, anyway, once again, this is simple harmonic motion.
So we see both of these. Minus k over m is the proportionality constant. Here, mgd over I is the proportionality constant. But they're both proportional to displacement. And that's the key thing. So without further proof, we've established that we really do have simple harmonic motion. However, once again, it's limited to the simplifications, the approximations that the simple pendulum was. Can't avoid that, really. So I know that's disappointing to us to some extent because we want perfect solutions, but get used to it. Now, therefore, k over m equals mgd over I. Omega is square root of k over m, so that's also equal to the square root of mgd over I. And omega equals, 2 pi f, and period is 1 over that, so 2 pi over omega. So we have period is 2 pi square root of I over mgd. And there is the period of a physical pendulum in terms of the moment of inertia, the gravitational tug, and the distance from the pivot point to the center of gravity. And I'm sorry, the length, that's not true, but the distance from the pivot point to the center of gravity, just purely. That's what d is. All right, let's move on. So now let's compare a simple pendulum and a physical pendulum directly, and we'll understand how they relate to each other from this simple example. They're going to be two pendulums, each a meter long and having equal mass. One is simple, the other is a meter stick, so it's not simple, but it does have uniform mass distribution. So first of all, we got the simple pendulum. A bob at the end, point mass at the end, 1 meter long. Gravity acts straight down in that. So there's the moment arm. The moment arm is across this whole length. The meter stick, same length. D is to the center of gravity, where mg is acting. So notice the moment arm is smaller. More torque over on the simple pendulum, right? Because at mg, you've got a bigger moment arm. Less torque on the meter stick. What about the moment of inertia? More over here, because the moment of inertia of this system is greater, because all the mass is distributed on the end. Less moment of inertia on the meter stick. Well, in fact, the moment of inertia of the meter stick is 1/3 ml squared. So if you think about it, these are antithetical in terms of what we're trying to accomplish, which is to see who wins, basically, which object is going to go through its oscillation quicker. That's winning. So the physical pendulum experiences less gravitational torque, but it also has less moment of inertia, smaller moment of inertia. So less torque, less moment. Those are going in opposite directions. Oh, less torque, but smaller moment doesn't take as much to accelerate it angularly. So who wins? The two variables has opposite effects. So you better tell me to demo this. Right now we'll just derive it. Have me demo it in class so you can see how we can prove what we're about to demonstrate with the equations. So for a simple pendulum, it's simple. Period is 2 pi squared root of L over G. And that applies to this system here. Physical pendulum, we just learned period is 2 pi squared root of I over mgd. Let's carry that out. 2 pi I is 1/3 ml squared. Big mg, that's the mg. D, 1/2 L, L over 2 to the line of action. We got some cancellations there. The m goes away, the L goes away. So the period of the physical pendulum is 2 pi squared root of 2/3 L over G. L over G, L over G, but 2/3. So this period is less. It's only square root of 2/3 what the other one is. So the meter stick has half the torque, but only 1/3 the moment of inertia. Therefore, the less moment of inertia, the fact that it has a smaller moment of inertia, only 1/3, more than compensates for only half the torque, and it still wins, reducing the period. So its period is less than the simple pendulum. So now let's do a little example. A thin-walled cylinder, but it's not pivoting about its center of axis, it's pivoting about the inside edge. Infinitesimal or negligible thickness of the wall. All right, so what's the period of oscillation? We've encountered this before, at least in terms of analyzing the moment of inertia, pivoting about that point. That's going to be important. So radius r from the center is where the axis of rotation is. Period 2 pi squared root of I over mgd. From the parallel axis theorem, I is ICM plus md squared, which is mr squared plus m, well, the distance from the pivot point to the center mass is r. So mr squared again, which is 2mr squared. So period 2 pi square root of 2mr squared over mgr. Some of that r and m stuff goes away, and we have the period for this system. Isn't it beautiful?